QA. Detecting which bug is challenge and kinds of which bug, such as sync frame bugs, for example, the floating text missing, and multi-frame bugs like pubs. And expand QA team is costly and inefficient. The supervised computer vision model is a potential solution for the which bug detection, but this supervised model needs large lab data set. And however, the real game bugs are rare and the annotated data is limited. So that's why we need to develop a data efficient and a scalable method to do the which bug detection in video games. So I listed the key contribution for this study. We proposed a hybrid co-fine-tuning method. We may call it as safety, and it has two parts: the co-supervised learning and the self-supervised learning. The co-supervised learning can use data from multiple games. They can combine the target and other game titles for bad generalization. And the self-supervised learning part, they can use unlabeled data. So it is data efficient. It can reduce dependence on large labeled data sets, and it can also utilize abundant unlabeled image. So here I show the proposed architecture, the safety architecture, and you can see from this figure it includes two parts: the co-supervised learning and the self-supervised learning, and it also has the backbone. Here we use the vision transformer. It can be any other model like ResNet, and we use the it also includes the detection head, and we use the fast RC and detection head. So I will introduce the two parts: the co-supervised modular and the self-supervised modular. So the co-supervised modular, it uses labeled data from target game and other game titles. So the labeled image from multiple titles can increase the diversity of which bugs and enhance performance. So, but they have some different. They have different importance between like the target game title and other game title. So during the loss calculation in the model, we add a hyperparameters alpha. So here, for example, this the loss of co-supervised part is the addition of a loss from the target title and the loss from the co-titles. The next one is the self-supervised module. And self-supervised module, they use unlabeled data from a target and the co-titles. And it do the masked patch reconstruction in the latent space. And for this part, the MSE is used, and the MSE loss is calculated between reconstructed and the target latent features. So it can be from this figure show the loss calculation for the self-supervised part. It's and here in this study, we mainly address the multi-frame which bugs. So basically, mainly it is pubs, and it includes like lots of detail pubs and calling pubs. I will give the example in the next slide about AIIDE pub and calling pub. And this table will show the number of labeled image and unlabeled image we used in this study from different game title. So here I show the example of a pub which box basically is calling pub and AIIDE pub. So calling pub, if there is when there is like abrupt appearance or disappearance of object in the scene, and this is a calling pub. And for the AIIDE pub, if there is like sound change in object detail or texture, so we can see the this example. So the calling pub, like so this time they show the object, for example, suddenly disappear. This kind of bug is called calling pub. And another one is AIIDE. Yeah, the next slide, the coming slides, we will show the results based on the 4 research questions. So this one, in this table, we show the results of safety and that from baseline. So here the auto ML, it means is the baseline, and the safety is the proposed method. And in this table, the like 100%, it means we use all of the data we have, like the lab data, and 50%, it means we use half of the data. And the alpha is the weights assigned within the co-supervised learning. They is defined in this loss equation, and the beta is the weights assigned to the self-supervised learning. So we try to study the mixing strategy, and in this table we can see like the beta is relatively stable compared with alpha, and also the alpha has a high variance. So it means that we should pay more attention to the alpha tuning, and for beta, maybe we can because it's more stable, we can just use a value like 0.2. But for alpha, they should carefully train when we try to train the safety model. So another one is the ablation study, and because this model includes 2 parts like co-supervised learning and self-supervised learning. We want to know, for example, their influence on the performance. So we incrementally add CSL and SSL components to determine their influence on performance. So this table, in this table, when it is say true, it means we include this component. When it's false, it means we exclude these components. And from this study, we can see the highest performance is observed when we do both like CSL and SSL. And at the same time, also we observe the lost performance when we exclude the two components. And also you will see when you check the results in this table, we can see like looks the CSL component is more important, but SSL also contribute the final performance. Yeah, the next one is about the generalization, and we want to because as I said, this study we focus on the multi-frame bugs, and we also want to apply this model to other bug types like the single-frame bugs. And here we use two kinds of single-frame bugs. The floating and the texture. The floating bugs is defined as object expected to rest on a surface appears suspended, leaving a visible gap. And the text bug is defined as like surface show blurry or low detail texture appear unnaturally strange or distorted. So this is the definition of floating and the texture. This is two typical single frame bugs. And in this table, we show the results from safety and the baseline auto ML. And we can also see, for example, the safety outperform auto ML, especially on the gentle map title. And the safety and the baseline show comparable performance on the high-res title. And for example, in the texture, also the safety show a better result. Yeah, so for this study, there still have some limitation, and so for example, it's pixel modality dependency. So it means it only rely on RGB input and lack rich vision cues like depth or segmentation. Because from our previous study, actually, like other model like depth is helpful for the rich bug detection. And there are no adaptive objective balance. So it means we need it requires a manual tuning of supervised and self-supervised weight like alpha and beta. And also another limitation is that is uniform code domain mixing, because it treats all code domain games equally during training. So in the code supervised learning, there are two parts like target title and other titles. Other titles, it means other title can include a lot of titles, but currently we just treat all other titles equally. But in reality, some title may contribute more. So currently we didn't do this kind of study. So then it means we can also have some future direction. Like we can learn shared embedding across modality like RGB, depth, or segmentation, and or even other modality. And also in the future we can develop adaptive data mixing strategy for game domain. And also currently for example for the multi-frame bugs, we only cover two kinds of pubs, LD pub and column pub. And actually there also has other bugs like the fighting or lighting. And yeah, we should in the future we may try to cover more bugs in this model, do more testing. Yeah, the key takeaway is so we propose a hybrid co-fine-tuning method, and it integrates like co-supervised and supervised learning. It can use both labeled and unlabeled data effectively, and it enables cross-game knowledge transfer. It leverages a code domain from multiple games to improve model robustness and generalization. And our results show the proposed method outperformed baseline across 3 game titles. Yeah, so overall impact is that safety, the enhanced performance, data efficiency, and cross-domain transfer, and it advanced automatic vision QA for video games. Yeah, thank you.
Yeah. The problem here is take these models to find going into getting from control. The other approach that the features
Yeah. So actually, we also tested the which language model for this study. So from our observation, yeah, current model, the safety the purpose one, get the best result. So for the which language model, so first we still need a lot of data for the fine tuning to fine tune the which language model. And yeah, from our result, if we just do the classification, yeah, the which language model we do the fine tuning, yeah, it get a good result. But when we do the object detection, we want to detect the exact bugs within the image. So in this case, it still need a lot of image.
And like looking at
yeah. So sorry, can you repeat your question? Yeah, definitely. I think in the future, as the method we propose, we hope, for example, if for like for vision language model or even for other models, we hope they use less and less data to do the bug detection. So I believe, yeah, in the future, I think a vision language model is still a good direction, but I think so how to use the unlapped data is very important for even for vision language model or for other supervised model. Yeah, I mean how to use the data is important. Yeah.
So I know that Microsoft and elsewhere for research you have the like you use projects for model, the logic model. Do you think at some point it would be possible for this approach to detect non-visual bugs? I mean, they do visual independent, they're like mechanical bugs, like guns, fire.
Yeah.
Do you think that would be possible to maintain?
Yeah, I think the procedure may not totally the same, but the idea I think is possible because the idea even for other bug types like here we focus the which bug types only maybe occupy around like 30% of the total bugs, and it's not that high. Yeah, it's still high 30%, and yeah, and I mean the idea can be applied to other game titles. Yeah, definitely, I think. Because the other bugs, they still have this kind of issue. We don't have a lot of left data. It's difficult to obtain this kind of data.
One last really quick question for me.
Yeah.
Have you used this at all in actual QA testing?
Yeah, this one we didn't deploy this in the production, but we did test this algorithm for other game title. I mean the real game title. Yeah.
Thanks again.
Yeah, thank you.